Hello everyone, my name is Tom Augsburger and I'm a software engineer at Anaconda where I get to work on open source libraries like Dask and Pandas and relevant today, Dask-ML. So today we're going to be looking at an example of ensemble learning with Dask-ML. Dask-ML helps with scalable machine learning along a couple of dimensions of scaling challenges. In this case, we're going to be considering a case where your data set is growing larger than memory. And so your typical tools like NumPy and Pandas and scikit-learn, they don't really deal with data sets that are larger than memory. And so that's where Dask and Dask-ML come in. We're going to see an example of how to use Dask-ML's ensemble methods to very quickly and efficiently train an estimator on a larger than memory data set. First of all, some background on ensemble methods. They're typically used to, the ensemble methods, the idea behind them, are useful for things like scikit-learn's bagging and random forest estimators, voting classifiers, those sorts of things, and also gradient boosted tree libraries like XGBoost or LightGBM. It's a very general idea. We're going to go ahead and connect to a small Dask cluster that's just running here on my laptop. I'll have 8 workers for this toy demo. In practice, if you're wanted to use these ensemble methods for real, you would want to connect to a large cluster that's able to, that's been deployed on multiple machines. Since, again, the idea is to work with a larger than memory data set. So we're gonna generate a data set here that's fits in memory on my laptop, again, just for this example. In practice, you would be reading in this data set from a database or S3 onto a cluster of machines. In this case, our data sets, it fits in memory just fine, but the important thing is it's been chunked into multiple chunks. So we have this Dask array. It's like a NumPy array, but it's been partitioned here into chunks. In this case, I think we have 10 chunks. All right, and now suppose that we want to use our classifier that we're familiar with, like scikit-learn's ridge classifier. However, we couldn't simply pass a larger than memory data set to ridge classifier. Scikit-learn would probably try and convert that into an in-memory NumPy array before it did anything with it. And that would end up, crashing your worker or your laptop or whatever machine you're working on. Since the NumPy arrays wouldn't be able to fit in memory, we can't actually use scikit-learn's ridge classifier on this data set. So instead, we're going to pair scikit-learn's ridge classifier with one of Dask-ML's ensemble methods. In this case, we'll be using Dask-ML's blockwise ensemble voting classifier. It's a bit of a mouthful. Okay, so the basic idea behind Dask-ML's ensemble methods is pretty similar to scikit-learn's voting classifier. The idea is to take a group of estimators and then train them somehow, which we'll get into in a second, and combine their predictions. So, when we get to prediction time, we'll say for row 0, for the first example, we'll ask each of the individual estimators, what do you think is the right prediction for this row? You'll ask estimator 1, estimator 2, estimator 3, and so on, and then somehow combine those predictions. In the case of classification, we'll be doing some sort of majority vote to pick the overall prediction for that row. The training is quite different, though, between scikit-learn's voting estimators and Dask-ML's blockwise voting estimators. So scikit-learn, the idea is to take several different kinds of estimators. You might have like a random forest and a logistic regression and maybe a ridge classifier, and you train each of those on the full data set. But that doesn't work here, remember. The idea is we have a larger than memory data set. We can't pass that full data set to a scikit-learn classifier. So instead, what Dask-ML's blockwise voting classifiers do is they take a base estimator, like scikit-learn's ridge classifier, and clone it a bunch of times, once per partition, and train each of those clones on one partition of the data set. And so that works out nicely because the partitions do fit in memory. They are, at the end of the day, just a NumPy array, so we know they fit in memory. And so we're able to actually complete training on each of these partitions. And then the job of the blockwise voting classifier is to combine the votes from each of those partitions when it comes to prediction time. So we'll go ahead and create our classifiers here. We have a base estimator from scikit-learn. This is our ridge classifier, and then we have the overall classifier here from Dask-ML. We'll go ahead and fit that, and we'll see a bit of activity. I'll talk about what's going on here in just a second, but we're training the overall estimator here. And that overall estimator is composed of many different base estimators. In this case, it's one per partition. So we have 10 clones of our base ridge classifier here. And each of those has been fit on one partition of the data set. So this really has been optimized for a couple of things. First of all, it's optimized to minimize transfer communication. So we're dealing with typically large data sets here. And so we don't want to be moving around a whole bunch of data, which is shown in red here. And you can see that once we have a partition of X and Y on the same data set, or sorry, on the same worker, we don't have to move data around. All we have to move around really is the small Python object that is the scikit-learn classifier. We move that to the worker, and then it trains on its partition. So we can go ahead and see that again. The communication here is shown in red, and that's just showing, really just moving around these small objects, these ridge classifier objects, which really are just the coefficients on the estimator. Okay, so that's showing how we fit it, and let's analyze that a bit. So these really are different estimators. They do generally learn different coefficients. So in this case, we're going to have our coefficients here. We have the X-tick label, or we're showing the difference in the coefficients between the first and the second classifier here. And you can see that generally they are learning different values for the coefficients. We can see that they produce different scores. So in this case, we're going to use, take a look at the scores for each of the estimators, and we're going to use the cluster to do that scoring in parallel, because why not? So we go ahead and score it on, map the score function over each of our estimators. And we see that, in general, the scores are between 0.645 and 0.2 and 0.6454. And the hope is that the overall estimator, CLF, does well on the full data set, which in this case it does do pretty well. It ends up being towards the high end. And in general, these ensemble methods are going to give lower variance predictions. So this ends up doing pretty well. However, it's not always going to go so smoothly. The idea behind this blockwise ensemble strategy is that each of the partitions are generally similar to each other. They're roughly uniform. And if that assumption is not true, then you'll actually end up doing really poorly when it comes to prediction time. So we're going to make an example data set where we don't have this nice property of uniformly distributed partitions. So in this case, we're going to define this little clone shift function. All it does is take some base array, add some bias to it. We'll see what this is coming from in a second, and some noise. And we'll do the same thing for the X and the Y. We'll go ahead and use, make some base data set here with scikit-learn's make regression. And then we'll use Dask delayed to call this clone and shift a bunch of times, once for each partition. So again, we're going to generate a data set here that has 10 partitions, only now they're not so uniformly distributed. So let's take a look at the distribution of the first feature, feature 0, and the target, Y here, across partitions. So the partition is, the color here is by partition. And you can see that as we increase the partition number, feature 0 is increasing and the target is increasing. This is an example of a data set where the partition, the data is not distributed uniformly across partitions. And so, we'll see in a second, blockwise, Dask-ML's blockwise voting classifier regressor may not be appropriate. We'll make a sub-estimator here. In this case, we're doing regression, and we'll wrap it with a blockwise voting regressor. And then we'll go ahead and fit it on this second data set that we generated. So that's our blockwise voting regressor. And we'll compare it with a second estimator, which is just using scikit-learn on a sample. Remember, the idea is that we want to use Dask-ML's ensemble methods if we want to use some sort of scikit-learn estimator on a data set that doesn't fit in memory. So supposing that this data doesn't fit in memory, but maybe a sample of it does, we'll take a sample here, in this case, 1/10 of the data set, and train the sub-estimator, the scikit-learn linear regression, on just that subset. And we'll see which one does better. In this case, it's the blockwise voting classifier regressor gets a score of -11, and the sub-estimator gets a score of 0.1-ish, 0.001, and 0.07. And in general, in scikit-learn, higher scores are always better. So the actual values here aren't too important. All that really matters is that higher is better. So we've seen that, despite seeing just 1/10 of the data and being a much simpler model, the scikit-learn estimator does much, much better than the Dask-ML blockwise ensemble estimator that was trained on the full data set. And that's just reflecting the fact that the blockwise ensemble method really is assuming that the data set is uniformly partitioned. So what do you actually do here? There's a couple of options. You might be able to introduce some sort of transformation into the data set to de-skew it, or you might be better off just shuffling the data, doing a complete random shuffle of the data before trying to use this ensemble method. It is worth reflecting, this could be a very common problem. So these data sets that you're reading in, there's a good chance that there's some sort of, that the partitioning of the data set is correlated with some of the features. If you think about some sort of batch system that's generating some data every day or every month, that's, the partitioning is going to be partitioned by time, which is often correlated with some feature or with some target. So it's worth keeping in mind. Other examples are things like partition by geographies, by state or county or something like that. This sort of partitioning structure is often going to be mirroring or correlated with some features of the data. So you really do need to be careful to watch out for these and make sure that your data is partitioned appropriately before reaching for one of these blockwise ensemble methods. Alrighty, thanks.